Yes. Good morning. Thank you very much for the introduction. Today in this presentation, we are going to discuss the seismic behavior of ancient colonnades interacting through a diaphragmatic roof. This particular study was carried out having as a case study the West Pteron roof of the Parthenon in the Athenian Acropolis. The Parthenon is an ancient Greek temple built in the 5th century BC. It's a peripteral, meaning with a colonnade surrounding the main temple, octa-style temple of the Doric order with Ionic architectural features. It is built with accurately fitted marble blocks in total absence of mortars. The only provision of connections is with the metal clamps and dowels for the blocks of the walls, the entablature, and the pediments. This is a graphical reconstruction of the temple carried out for numerical modeling purposes. Here we can see the layout of the marble coffered roofs. You can see my pointer here, maybe, or not. Okay. Those roofs are vividly depicted in these drawings by Professor Manolis Kores. Here is the area under consideration in this study, depicted in blue. And from this section, it is obvious that the coffered roofs bridge the two colonnades of the outer colonnade and the inner colonnade of the temple. We must note that though the beams are connected horizontally to each other with typical double T metal connectors, and the coffers are doweled to the beams vertically, the beams themselves rest on the entablature of the colonnades without being attached to them. Thus, they can freely slide. The provided seating is approximately 30 centimeters in the outer colonnade and 60 centimeters in the inner colonnade. But the structure has not reached modern times intact, as was seen in the graphical reconstructions. The monument has undergone various disasters, both natural, like the earthquakes that struck the temple, and man-imposed as the fire of the 30th century AD and the explosion of the 17th century, alongside with extensive repairs and functional renovations in its long course. I would like to make a special note on the fire of the 3rd century, because it is the first extensive damage on the under consideration area of the West Pteron roof. The wooden part of the roof and the tiling was completely destroyed. The marble coffered suffered great damage, and the coffer slabs were severely fractured, and some of the remnants must have been demolished for safety reasons. Only the beams survived in their original position, though fractured. The repairs of Emperor Julian in the 4th century AD, where a new roof was provided for the temple, included only the main cella, and the Pteron was left unroofed. From the fire on, the West Pteron remains without a roof structure until today. The temple, though with many alterations, reached the 17th century as a whole. And the September 9th of 1687, the blast was the biggest catastrophic event of the temple that left the building in ruins. It seemed that the state of preservation of the West Pteron little had changed from 1805 until the first organized efforts to preserve and restore buildings on the Acropolis began in 1985 with the formation of the Committee of the Acropolis restoration monuments. Though the previous scholars and historic restorers, Nikolaos Balanos and Anastasios Orlandos, had already prepared new marble architectural members for restoring the coffered roof, those projects were never carried out. Here, the preservation state of the beams, as was found in 1992, is presented. The beams were then dismantled in order to carry out the restoration of the opisthonios. And the discussion for the restoration of the coffered roof began, with this architectural proposal being one under consideration as the bare minimum to restore what was dismantled for the restoration works. The next proposal was to restore the full grid beam layout, incorporating some prepared material by Anastasios Orlandos, and with minimum use of new material. Another consideration was restoring two of the south interspaces of beams with covered slabs. And the last one was fully restoring the covered roof of the West Teron. This particular restoration proposal fully exploits the prefabricated marble architectural members by the former restorers of the temple. Though the full restoration of the roof was plausible, bared enormous educational value and restored a long-lost image of the ancient temple, giving the next generation a glimpse of the past, and would also compensate for the preparation of the historic architectural members, yet the condition of the columns of the opisthonios raised great concern as to if the rehabilitation that was carried out with sole grout injections and no other type of reinforcement, like titanium bars, was sufficient for the monument to withstand the seismic forces that the temple will have to endure. Thus, a preliminary study was carried out to assess the contribution of the coffered roof in the seismic behavior of the independent colonnades during seismic events. Intuitively, a diaphragmatic behavior of the roof was expected, providing some kind of interaction between the independent colonnades. In order to assess the seismic risk and overall effect of the roof, the construction was modeled using the discrete element method and using the 3-deck code of Itasca. And the analysis was with numerical modeling of the whole temple. Those models were calibrated using real accelerograms obtained by an installed accelerometric array in collaboration with the Geodynamic Institute of the National Observatory of Athens and the Acropolis Restoration Service. The calibration procedure consisted of using as input the base registration and comparing the output on the top of the column with its respective registration. The parameters of the model were defined as damping equal to 3% and a period of 6 seconds. Having calibrated the models, we could use them to establish some preliminary results on the overall behavior of the restoration proposals for the roof. The first model in the current is the current state of the monument, meaning without the beams, as those were dismantled in 1992. The second model accounts for the full restoration of the grid of beams. And the third model accounts for the full restoration of the coffered roof. As this was just a preliminary study that wouldn't account for the damages of the columns, 3 solid models were needed for comparison reasons, and some of the actual architectural proposals were not considered. The numerical models include the actual number of architectural blocks without the damages, rigid blocks, and well-fitted together closed joints. The base of the structure was considered rigid and uniform in the level of the pavement. According to the method used, every architectural block is considered as individual and rigid, while all the deformations occur in the joints, in the interfaces, meaning of the blocks. The seismic events selected were chosen to correspond to the worst-case earthquake that could have occurred in Athens in more than 2,000 years, and 9 appropriate actual accelerogram of strong ground motion suitably amplified were considered. The time histories records of critical architectural members, here shown in red, were compared and evaluated for each seismic event investigated separately. The investigation focused on crucial members' behavior, such as capitals, architraves, pediment blocks, the roof beams, and the roof coffers. As for the results, no severe damage, meaning collapses, were predicted by the numerical models that were analyzed, confirming that the sitting of the beams freely, resting on the entablature, is sufficient. Something that we were expecting since the beams survived on the monument for many, almost 18 centuries without any damage. Among the conclusions of the current study, it can be ascertained that there is an inherent sensitivity of such models on the frequency content of the ground excitation used, which is depicted by the lack of systematic members' behavior and the inconsistency between maximum and permanent displacement with the seismic excitation. Those are actually results that have been presented in other similar studies. For example, here are the displacements plotted for the same capital under different excitations. Here, the 2 selected registrations of the Campano-Lugano earthquake are presented. It can be noted that the 2 registrations bear different number of pulses, and the effect on the structure varies significantly in terms of maximum displacement magnitude, though both registrations are normalized to represent earthquake magnitudes of the same return periods. In this particular case, even the axis of the maximum displacement is different for the 2 registrations. Furthermore, a significant amplification can be noted for the case of the freestanding colonnades, which is much more obvious for the case of the Bisaccia registration, and the out-of-plane axis of the colonnade, here depicted in light blue. The same observations can be made for the 2 registrations of the Northridge earthquake presented in this plot. The 2 registrations bear different number of pulses, and the effect on the structure varies significantly in terms of maximum displacement's magnitude. Whereas the 3rd registration of the same earthquake demonstrates a significant higher ratio of amplification for the case of the freestanding colonnades and the out-of-plane axis of the colonnade, which is here depicted in light blue. Here, the displacements for 2 different earthquakes registrations are plotted. Though they differ in displacement magnitude, it is obvious an amplification, as well as before, of the freestanding colonnades and the out-of-plane axis of the colonnade. It is important to note that the amplification ratio is lower in the range of maximum displacements. Here, the displacements for 2 different earthquakes registrations from the area of Greece are plotted. The most significant displacements occur for the out-of-plane axis of the colonnade. The characteristic amplification for the case of the freestanding colonnades and the out-of-plane axis of the colonnade can also be noted, but again, for the case of the most severe in terms of displacement registration, which is the Athens earthquake, the phenomenon is declining. In particular, architectural blocks, a systematic behavior seems to remain constant in all the investigated ground motions and scenarios. For example, the tendency of the outer peristasis capitals, and we tend to suspect also the columns. There's a tendency of leaning outwards at the angle of the temple. Furthermore, the general behavior of the lengthening of the facade, demonstrated by the opening of the joints at the architrave level and at the pediment blocks level, was also observed. Both tendencies are verified by the actual deformations that are present in the monument. The models confirm that the roof tends to restrain the overall displacements of the structure, especially where the maximum displacements appear towards the center of the facade, whereas the grid of beams scenario tends to amplify the displacements for the upper blocks of the structure. Here, for the Athens earthquake, the displacement plots for both of the northern DD1 and the center beam DD4 are presented. It can be noted that the scenario for the full roof restoration retains the displacements that tend to lean towards the west and south in the case of the restoration of the grid of beams. The grid of beams being with the lighter colors depicted. Thus, the addition of the coffered slabs actually provides a diaphragm, readjusting the displacements of the two colonnades. This was the preliminary study, and as for the next steps, we are hoping that we could actually model the fractures of the columns, presented in the columns, and have some assessment for those fractures. Thank you very much for your attention.